So in this video, I'm going to introduce a new concept of, we're going to deal with rational functions, being able to analyze them, find out some of the key points of their graph, like X-Intercepts, Y-Intercepts, Asymptotes, talk about end behavior, talk about domain, range, that kind of stuff. But before we jump into that, we're going to tap into some things we already know, so I'm going to remind you about them. So we're going to use some things we learned from the polynomials, and we're going to learn something we know about these two parent functions, because these are the two parent functions that go with the these are the parents of the rational functions. So you can see that there's fractions involved here. So a rational function is a function that's made up of a polynomial divided by a polynomial. And that's why we want to use some stuff for polynomials. So the first thing we're going to use is the concept of end behavior. So I'll just review that real quick. End behavior. How do we know end behavior of polynomials? So if you're looking at a polynomial like y equals 3x to the 5th plus 7x squared minus 7, x plus 2, let's say. So really, I just need to know two things about a polynomial to determine its end behavior. I need to know the degree of the polynomial, and basically whether it's odd or even, and whether the leading coefficient is positive or negative. So this is a positive leading coefficient, and it's a 5th degree. So just from that knowledge, I know that this thing is going to be negative infinity on the left, positive infinity on the right. And the formal way we write that is the limit of y as x approaches infinity, that would be on the right, is positive infinity. And the limit of y as x approaches negative infinity would be negative infinity. So again, another way to write this would be on the right, positive infinity, on the left, negative infinity. Okay, should be able to make the connection. See how this is saying that we're going on the right? This is saying we're going to the left? Okay. So that's one bit of about the polynomials that we need to understand. The other thing about polynomials is we learned that the roots of a polynomial are connected to the factors of a polynomial. So if we have a polynomial in factored form, like x plus 2 times x minus 3 times x plus 1 squared, let's say, this thing has roots at negative 2 because of that, positive 3 because of that, and negative 1 because of this last one. And there's something special happening with negative 1. We say it has a multiplicity of 2. Because the factor that produces negative 1 occurs twice. And remember, there's something special that happens when it has a multiplicity of 2. These are also X-intercepts. And this x for negative 2, the graph will just shoot straight across. For 3, the graph will shoot straight across. And negative 1, because it has a multiplicity of 2, the graph actually comes down and hits the x-axis and bounces off. So it looks basically like a parabola sitting on the x-axis. Okay, so that's the two concepts from polynomials that are important for us to understand. The end behavior and the connection between roots and factors. Okay, and remember, roots just means the numbers that make the equation equal to 0 when you plug them in for x. So negative 2 is a root connected to this factor, because when I plug negative 2 in for x, negative 2 plus 2 is 0. Okay, so that's what we need for polynomials. Now, from what we know from these parent functions, if you remember, y equals 1 over x looks like this. And these are kind of unique because they introduce things we've never seen before. So for example, this guy, and I guess I'll write the other one, y equals 1 over x squared. That guy looks like this. Okay, so what we can gather from this is, first of all, they have vertical asymptotes. They both have a vertical asymptote at y equals, or at x equals 0. And that's not surprising because when you plug in 0 for x, we get undefined. Same thing here. When we plug in 0 for x, we get undefined. So these have vertical asymptotes at on the y-axis, or at x equals 0. They also have what are called horizontal asymptotes. We've talked about the end behavior of these things. The end behavior of 1 over x. In other words, what happens to the y's as x goes way out to the right? Well, you can see the y's are coming down and they're getting closer and closer to 0. And over on this side, they're coming up and getting closer and closer to 0. So we would say that this thing has a horizontal asymptote at y equals 0. They have a vertical asymptote at x equals 0. And if you think about it for a second, if we were to move this thing to the right 2, you would say this would be y equals 1 over x minus 2, right? So I'd move it to the right 2. And so we know that this thing would look like this. And so notice that the asymptote just moved to the right 2. So notice, more importantly, that the asymptote is in the location of the root of the bottom. You see that? See, the roots of the bottom up here are 0. The roots of the bottom down here are 2. So the root of the bottom is telling me where the asymptote is, because it's causing me to divide by 0. If I have a 0 on the bottom of a fraction, I'm going to divide by 0, which gives me undefined, which is going to produce an asymptote, potentially. Okay, so that's the two concepts we need to understand. We need to understand what I said about polynomials and what I just said about one other thing, sorry. The behavior around the y and the vertical asymptote. Notice on this one that the behavior is different on either side of the vertical asymptote. On the right side it's going up, and on the left side it's going down. But on this one, the behavior on either side of the asymptote is the same. They're both going towards positive infinity. And notice that 0 here has the root of both these are 0, but here 0 has a multiplicity of 1 as a root, and here 0 has a multiplicity of 2 as a root. So again, the takeaway from that is just like when we have greater than 1 multiplicity on X-intercepts, it produces something. Same thing as when we're dealing with zeros on the bottom. Okay, so now we're going to take all the information and apply it to an actual rational function. Okay, so here's a rational function, and we want to analyze it. We want to find a bunch of information about it, and then we're going to try to graph it just from off the top of our heads. So we're going to use the information we just learned. So we know that the roots of a polynomial produce X-intercepts in a polynomial, but with a rational function, it's not quite the same, because if we have roots of the bottom polynomial, that means I'm going to have 0 on the bottom, which means we'll get undefined. But if I have roots at the top, that would make the overall fraction 0, so that would produce X-intercepts. Okay, so usually the first thing we're going to want to do is find out the roots of the top and bottom of a rational function. And of course, it's much easier to find roots if it's factored. So the first thing I would do is factor this. And this is going to be 3 times x minus 3 times x plus 3. And down here, we're going to have an x and an x, and that would be 2 and 3 and plus and plus. Okay, so we got it in factor form, and then we ask ourselves, what are the roots? So the roots of the top, or the zeros of the top, would be 3 and negative 3, because 3 makes this factor 0, negative 3 makes that factor 0, and there's no way to make this factor 0. So the roots would just be 3 and negative 3. Okay? Roots on the bottom. That would be negative 2 and negative 3. Okay. So First of all, these roots on the bottom, -2 and -3, are going to be a problem, right? They produce, they're forcing us to divide by 0, which means they're not a part of the domain. So if we were to write the domain of this function, we would write, goes from -infinity to -3, and then from -3 to -2, and then from -2 to +infinity. Or another way to write that is all real numbers x not equal to -3 or -2. Okay, so that would be the domain. Because these things are not a part of the domain because they force us to divide by 0. Okay, but we want to know more than that. We want to know how they affect the graph. So I want you, this is really important to pay attention to this. So, well, I guess everything I'm saying is important, but I want to especially draw your attention to this. Notice that x plus 3 is the same on the top and the bottom, which just shows up here where they have the same root, okay? So that's a problem because this is not going to produce an x-intercept because we know that 0 divided by 0 is undefined, okay? So this 0 on the top will produce an x-intercept. This 0 on the bottom will produce an asymptote because it's just like the 1 over x and the 1 over x squared. But when we have a 0 on top and bottom, we need to figure out what that does. So see if you can follow this. X plus 3 divided by x plus 3 is going to be 1 everywhere except at -3. Because if I plug in a 1 for x, I get 4 over 4. If I plug in 2 for x, I get 5 over 5. If I put a 10 for x, I get 13 over 13. So this thing is always 1, except for when I plug in -3 for x, I get 0 over 0, which is not 1. It's undefined. So essentially, what I'm trying to point out here is that this function, this guy that we're working with, and this function are exactly the same everywhere except at x equals -3. Because if this thing is, if the yellow is always 1, it'd be just like having a 1 here, right? 1 times that. So this function and this function are exactly the same everywhere except for at x equals -3. So, and what happens at x equals -3? It's undefined. So essentially what it does is it produces a hole. So in this case, under my domain, I'm going to have a vertical asymptote at x equals -2, and I'm going to have a hole at x equals -3. So remember what a hole looks like. The graph comes up to it, hops over it, and keeps going, and we usually represent that by putting a really bigger than the hole is because it's just 1 point, but that's our way of signifying there's a little skip there, okay? So let's summarize that. If you have a root of the bottom and it's only a root of the bottom, it'll produce a vertical asymptote. If you have a root of the bottom that's also a root of the top, then that'll produce a hole. And finally, if you have a root that's just to the top, that'll produce an x-intercept because 0 on top of a fraction is equal to 0. Okay, so let's move on here. So if we wanted to find the x-intercepts, it's just x equals 3, so that'd be 3, 0. We could also find the y-intercept. See, if we plug in 0 for x, it looks like we get -27 over 6. So that would be, what? -9 over 2. So there's y-intercept. And let's go and draw this thing, at least begin to draw it. Okay, so there's my xy plane. And we said there's an asymptote at -2. So there should be a dotted line here. We have a x-intercept at 3, 1, 2, 3. We have a y-intercept at 0, negative, that would be 4.5. 1, 2, 3, 4.5. So it'd be right down there. And we have a hole at -3. We didn't find out where that was. So if we want to find out where the hole is, okay, obviously it's -3 something, but, and we can find that. Now, follow this closely. Notice we don't want to plug it in here, because if I plug a -3 in there, I'll get 0 over 0, which would be undefined. So, but since we said this graph is just like that everywhere except for at -3, we could just plug -3 in here to find out, because this will have a point where this has a hole. So I plug -3 in there, and I get 3 times -6, which would be -18, and plug a -3 in there, and I get -1. So this would be 3, 18. So that means I have a hole way up here somewhere. Okay? Okay, now we got to fill in some stuff. So, very important concept. If I have a graph and it changes from positive to negative, you're going to see it cross, right? Because it'll be an x-intercept, unless there's a discontinuity there. For example, with a vertical asymptote, it's possible to be on the bottom, below the x-axis, and then on the other side of the asymptote to suddenly be on the top. So if we're trying to, basically what we're doing right now is figure out where the graph is above the x-axis and where it is below, because that'll help us draw it. We want to keep that in mind, that the only place it can cross the x-axis is at x-intercepts or at vertical asymptotes. The other thing to keep in mind is when you get close to a vertical asymptote, the graph only has two choices. It is either going to head down towards negative infinity or go up towards positive infinity. That's the only choices when you come close to a vertical asymptote. So in this case, since I'm already down here, my choices would be to turn and go back up, but then I would see it cross the x-axis, so that's not possible. So this thing must just keep going and head down. Likewise, it's got to come up and hit here, right? Because it's got to go through there. And we know that it crosses, it doesn't bounce off, because the multiplicity of 3 is just 1. And from there, we're not sure where it goes. We'll just leave that alone for a moment. Okay? Now, like I said, remember that with 1 over x, the behavior on either side of the asymptote was different, because there's a multiplicity of 1 there. So once again, this root, the -2, has a multiplicity of 1. So we know that the behavior on either side of this asymptote should be different. And now that's not surprising, because we already know there's a hole up here, right? So the graph does go up to the hole and just skips over it. So it would have to be up here because of the hole. But it also has to be up there because I'm down here on the other side. And the behavior on either side of the asymptote has to be different because the multiplicity of -2 is just 1. Okay? Now we just got to finish off. We don't know where it goes from here. And of course, that is going to be answered by looking at in behavior. So we'll talk about in behavior, then we'll come back and finish that graph. In behavior, all has to do with the degree of the polynomial. Just like in polynomials, remember we know we can determine the degree of a polynomial by we can determine the degree of a polynomial. We can determine the in behavior of a polynomial just by knowing whether this degree is odd or even and whether its leading coefficient is negative or positive. So it's a similar case with rational functions. There's really 3 cases. So case 1, the degree on top is less. So because rational functions are made up of a polynomial divided by a polynomial, we can talk about the degree of the top versus the degree of the bottom. So, of course, our parent functions fall into this category, right? Y equals 1 over x, y equals 1 over x squared. Those are both, the degree on top is 0. In this case, the degree on the bottom is 1. And in this case, the degree on the bottom is 2. So these would be both examples of where the degree on top is less. What's the in behavior of both of these? The in behavior is horizontal asymptote at y equals 0. And so this is the end behavior of any rational function who has the degree on the top less. So for example, y equals 3x squared plus 7x minus 2 divided by 5x to the fourth plus 7. Notice the degree on top is 2, the degree on the bottom is 4. So this has a degree on the top less, which means in behavior-wise it's going to be headed towards 0, which means it has a horizontal asymptote of y equals 0. Now, if we go back to our original one, that's not the case up here, right? The degree on top is not less. In fact, the degree on top is the same, right? You have second degree on top and second degree on the bottom. So that is the second case. So it's case 1, case 2. Degree on top and bottom are the same. So the examples of that would be y equals 3x squared plus 2 over x squared, for example, or y equals 15x to the fourth minus 100 over 3x to the fourth plus 2x cubed minus 73, etc. So again, notice it doesn't really matter what the rest of the polynomial is, we're just looking at the degree. So the degree on top is 2, the degree on the bottom is 2. The degree on top is 4, the degree on the bottom is 4. So think about this. If you're plugging in bigger and bigger numbers for x, because that's what we do when we look at in behavior, then x squared is going to be, or 3x squared is going to be much more significant than 2. Right? When I plug in 1 here, I get 3 plus 2 is 5 over 1. Okay? But when I plug a million here, I basically get 3 million squared plus 2 over 3 million squared. Or over a million squared, I mean. So really what happens as x gets bigger and bigger, this becomes the dominating feature and this becomes insignificant. So really, and notice these are really the same, just that this one's 3 times as bigger. So what happens is the overall fraction gets closer and closer to 3. Likewise here, this becomes the dominating feature, the bigger numbers we plug in. So this overall fraction gets closer and closer to the ratio of these two leading terms. So in this case, we'd be headed towards a horizontal asymptote at y equals 3. And in this case, we'd be headed at a horizontal asymptote at y equals 5, because that's the ratio of leading coefficients. So when the degree on top and bottom are the same, then we have a horizontal asymptote at y equals the ratio of the leading coefficients. Okay, so if we go back up to our original guy, that is a case 2, isn't it? So it looks like the ratio of the leading coefficients would be 3. So this thing has a horizontal asymptote at y equals 3. So if you go up to 1, 2, 3, put a little dotted line, that really makes sense to what we've already got drawn, doesn't it? You can see this thing going up and flattening out. This thing coming down and flattening out. And that is the graph. So if you were to take this graph, or this equation, and plug it into y equals on your calculator, and graph it, it should look something like this. The hole won't show up because calculators don't have handle holes, and they won't draw. They might draw in the asymptote, which would be confusing, so it might look like this kind of, But if you graph it on a graph calculator, you should see it looking something like that. It's definitely having a y-intercept there and an x-intercept there, and some of those kind of things. Okay, and then so finally, let's do case 3. I didn't need it for this one, but we'll need it later. Case 3, and guess what that is? That's right. Degree on top is greater. Okay, what happens when degree on top is greater? Well, examples of that would be y equals 3x to the 5th minus 4x squared plus 2 over 4x to the 3rd minus 7, or y equals 3x squared plus 2x minus 4 over x plus 1. So notice in both of these, the degree on top is greater. Here, the degree is on top is 5, and the degree on the bottom is 3. Here, the degree on top is 2, the degree on the bottom is 1. So both of these fit into the third case. And when you have in this case, what happens is, and this is kind of a cool thing, that essentially, similar to the last one, it behaves like these guys, because as the x's get bigger and bigger, those become dominating feature. And notice that 3x to the 5th divided by 4x to the 3rd is really 3/4 x squared, isn't it? So what we're saying is, in behavior-wise, not the rest of the graph, but in behavior-wise, this rational function is going to behave like a positive quadratic. Okay, which means it's going to be positive infinity on the right, left, and positive infinity on the right. So we go over here and notice this thing is, if we just look at that the two leading terms, this thing is going to behave like 3x, because that's what you get when you reduce it. So this is going to behave like a line. So again, it'll be positive infinity on the right, negative infinity on the left. Going down over here and going up over here. Okay, so if once you've watched this and taken notes on it and feel like you have an understanding, you should go download the rational functions worksheet, and I have a video working through that. And again, I think it's beneficial to open up the video and work through the worksheet, do a problem, check your work, do a problem, check your work, etc. All right.